Implementation of Mars Sample Return Mission by 2026. Overview. The Mars Sample Return Mission MSR, a groundbreaking initiative spearheaded by NASA in conjunction with the European Space Agency ESA and the Japan Aerospace Exploration Agency JAXA, is designed to return Martian soil samples to Earth by 2026. This ambitious project is allocated a budget of approximately $3.1 billion and is structured into 4 critical phases focused on innovative design and robust international collaboration. Key phases of the Mars Sample Return Mission. Phase 1, Sample Collection ongoing, 2026. The mission's first phase involves the Perseverance rover, which successfully landed on Mars in February 2021. Since its landing, Perseverance has been diligently collecting soil samples from various locations on the Martian surface. The main objective during this phase is to gather scientifically relevant samples that can provide insights into Mars geology and its potential for past life. The rover is equipped with sophisticated instruments designed to analyze the soil and select the most promising samples for future retrieval. Phase 2, Sample Retrieval 2027 to 2030. Following the collection of samples, the next phase will focus on retrieving these samples from Mars. This unprecedented undertaking necessitates the development of a dedicated mission that includes launching a rocket from the Martian surface, a feat never previously accomplished. NASA is actively seeking innovative proposals from industry and research organizations to devise effective and cost-efficient solutions for this complex engineering challenge. This phase will test new technologies and methodologies to ensure the safe and successful retrieval of Martian samples. Phase 3, Sample Return 2030. Once the samples are successfully retrieved, they will be launched from Mars back to Earth. This phase involves collaboration among international partners to ensure safe transportation over a distance of approximately 33 million miles. The challenges in this phase include ensuring the integrity of the samples during transit and developing the necessary technology to facilitate a safe landing on Earth. Phase 4, Analysis and Research post-2030. Upon arrival on Earth, the Martian samples will undergo extensive analysis in various laboratories. This research aims to answer pivotal questions regarding Martian geology, climate, and the potential for life on the planet. The insights gained from the samples will also be crucial in planning future human exploration missions to Mars. The analysis phase represents a critical opportunity for scientists to deepen their understanding of Mars and its capacity to support life. Common themes across sources. International collaboration. A notable aspect of the Mars Sample Return Mission is the strong collaboration among NASA, ESA, JAXA, and various other international partners. The establishment of the International Mars Architecture for Return of Samples IMARS Task Force aims to coordinate these collaborative efforts. This teamwork promotes a unified approach to achieving the mission's ambitious goals, ensuring that expertise and resources are shared effectively across international boundaries. Budget constraints and innovation. Managing costs while maintaining the mission's ambitious objectives is a common theme in discussions surrounding the MSR. NASA has indicated a revised budget of $8 to $11 billion for the overall project, emphasizing the necessity of innovative engineering solutions to achieve mission goals without excessive spending. The emphasis on reducing mission complexity reflects a strategic approach to resource management, ensuring that all scientific objectives can be met within budgetary constraints. Scientific priorities. There is a shared recognition among collaborating organizations regarding the scientific significance of the Mars Sample Return Mission. The ability to analyze Martian soil in Earth-based laboratories is viewed as essential for advancing knowledge about Mars' history and its potential to support life. The mission is not merely a return of samples, it represents a critical step forward in planetary science and exploration. Differences between sources. Budget figures. While some sources specifically mention a budget allocation of $3.1 billion, others, particularly NASA's communications, indicate a broader budget range of $8 to $11 billion for the entire project. This discrepancy reflects ongoing discussions about costs and funding, highlighting the complexities involved in budgeting for a mission of this scale. Mission timeline. There are variations in the projected timeline for the sample return. Some sources suggest an earlier return date in the 2030s, while NASA's statements indicate a longer timeline extending potentially to 2040 under current constraints. This divergence underscores the challenges in maintaining ambitious timelines in the face of technical and budgetary hurdles. Technical details. Different sources provide varying levels of technical detail regarding mission architecture and engineering challenges. ESA tends to focus on international collaboration and scientific objectives, whereas NASA emphasizes logistical and budgetary considerations. This divergence in focus illustrates the multifaceted nature of the mission and the different priorities of the involved agencies. Conclusion. The Mars Sample Return mission is poised to represent a monumental leap in planetary exploration, merging cutting-edge technology, international collaboration, and an ambitious scientific agenda. As plans continue to evolve, the mission's success will hinge on innovative solutions, effective resource management, and the ability to overcome unprecedented engineering challenges. The insights gained from the Martian samples will not only enhance our understanding of Mars but will also inform future exploration efforts, ultimately paving the way for human missions to the Red Planet. The collaborative efforts of NASA, ESA, JAXA, and other international partners highlight the global commitment to advancing our knowledge of the cosmos and the potential for life beyond Earth. As we move forward, the Mars Sample Return mission stands as a testament to human ingenuity and our relentless pursuit of exploration. The Mars Sample Return Mission (MSR) is a complex and ambitious endeavor that has garnered attention due to its significant scientific goals, international collaboration, and intricate engineering challenges. Here are several counterintuitive insights drawn from the mission's implementation plan. 1. Budget discrepancies. While the mission has a budget allocation of $3.1 billion, various sources, particularly NASA, suggest a broader budget range of $8 to $11 billion for the entire project. This discrepancy indicates that initial estimates can greatly differ from later projections, often due to unforeseen complexities or changes in mission scope. The perception that a mission can be executed within a limited budget can be misleading, as the realities of space exploration frequently inflate the costs. 2. Timeline ambiguity. The mission is aimed for a sample return by 2026. Yet sources cite a potential return date extending to 2040 under current constraints. This highlights a common issue in space missions where ambitious timelines can shift dramatically. It's counterintuitive to think that a mission designed for a specific deadline may take years longer due to engineering challenges and budgetary constraints. 3. Innovative solutions for old problems. The mission's requirement for a rocket launch from Mars marks an unprecedented engineering feat. While one might assume that advancements in technology would simplify such tasks, it is often the case that innovative solutions are needed to tackle age-old problems. The need to seek out cost-effective and efficient methods to accomplish this task underlines the complexity of space exploration, where traditional methods may not suffice. 4. International collaboration complexity. While international collaboration is often highlighted as a strength of the mission, it also introduces layers of complexity. Different agencies, NASA, ESA, and JAXA, come with varying priorities, budgetary constraints, and technological capabilities. This can lead to conflicts or delays that might be counterintuitive to the idea that collaboration inherently streamlines processes. Instead, it often requires extensive coordination and compromise. 5. Scientific priorities versus budget management. The mission's scientific goals are ambitious, aiming to answer fundamental questions about Mars geology and potential for life. However, the necessity of managing costs can lead to compromises in scientific aspirations. The tension between pursuing groundbreaking scientific research and adhering to budget limitations can result in decisions that may not align with the original scientific vision, which seems counterintuitive in a field where exploration and discovery are paramount. 6. Public perception of risk. The complexities involved in launching a rocket from Mars and safely returning samples may lead the public to perceive this mission as overly risky. However, the reality is that space agencies often have extensive experience and protocols in place to manage such risks. The counterintuitive aspect here lies in the fact that what appears to be a high-risk endeavor is often mitigated by rigorous planning and past experiences which may not be visible to the general public. 7. Delayed gratification in science. The long timeline for sample analysis post-return after 2030 can be counterintuitive given the expectation that science should yield immediate results. The reality is that thorough analysis of Martian samples requires extensive research infrastructure and time, which may conflict with public expectations for prompt discoveries from such missions. 8. Engineering complexity and simplicity. The mission aims to reduce complexity in its design. Yet the inherent nature of space missions often involves sophisticated engineering solutions to seemingly simple tasks like collecting soil samples. This counterintuitive reality suggests that efforts to streamline missions may inadvertently introduce new complexities. 9. Potential for over-optimism. Initial projections about timelines and budgets may reflect an optimism that does not account for the myriad challenges encountered during mission development. While agencies often exhibit confidence in their plans, the counterintuitive truth is that space missions frequently face unexpected hurdles that can delay progress and inflate costs. 10. Impact of independent reviews. The role of independent reviews in shaping mission plans may seem bureaucratic, but they are essential for ensuring mission viability. The counterintuitive aspect is that such oversight can lead to necessary adjustments that ultimately enhance the mission's success, even if they initially appear as setbacks or obstacles to progress. In conclusion, the Mars Sample Return mission embodies numerous counterintuitive elements inherent in the complexities of space exploration. From budgetary challenges to the intricacies of international collaboration, the mission serves as a reminder that the path to understanding Mars is fraught with unexpected twists and turns, reflecting the unpredictable nature of scientific discovery. The Mars Sample Return Mission (MSR) is poised to become a landmark achievement in planetary science and exploration, yet several crucial elements within the mission details are often overlooked. Understanding these nuances can illuminate their significance for the broader context of space exploration science and international collaboration. 1. Complexity of sample retrieval. One of the most significant yet understated aspects of the MSR is the engineering challenge of launching a rocket from Mars to return samples to Earth. This task is unprecedented and involves intricate logistical planning and innovative engineering solutions. While many discussions focus on the overall timeline and budget, the technical hurdles inherent in launching a rocket from the Martian surface are monumental. Significance. This aspect is crucial because it not only reflects on the technological capabilities of current aerospace engineering but also sets a precedent for future interplanetary missions. Understanding the complexities involved can help stakeholders appreciate the risks and challenges that could impact mission timelines and budgets. Successfully executing this phase could pave the way for future missions to other celestial bodies. 2. International collaboration through IMARS. The formation of the International Mars Architecture for Return of Samples IMARS Task Force exemplifies the significant role of international cooperation in the MSR. While many may acknowledge the collaboration between NASA, ESA, and JAXA, the full implications of IMARS are often overlooked. This collective effort involves representatives from multiple countries and emphasizes a unified approach to planetary exploration. Significance. The collaborative structure established by IMARS can serve as a model for future international space endeavors. It underscores the importance of sharing resources, knowledge, and expertise to achieve common scientific goals. Furthermore, the potential for geopolitical implications cannot be ignored, successful collaboration may foster peaceful relationships and shared scientific interests among nations. 3. Budget dynamics and innovation needs. The budget figures associated with the MSR are often misunderstood or oversimplified. While the $3.1 billion figure is a focal point, ongoing discussions reveal a broader budget range of $8 to $11 billion that encompasses the entire project lifecycle. Moreover, the need for innovative solutions to manage costs effectively is a recurring theme but is often overshadowed by discussions on the mission's scientific objectives. Significance: the financial aspect is pivotal in shaping the mission's feasibility and timeline. Understanding how budget constraints drive decision-making can illuminate the challenges that the mission may face. The necessity for innovation not only pertains to engineering but also to project management and operational strategies. For instance, fostering innovation could lead to cost savings that would allow for earlier sample return dates or expanded scientific investigations. 4. Scientific priorities and future implications. The mission's scientific objectives are frequently highlighted. Yet the broader implications of returning Martian soil samples to Earth are often not fully appreciated. The potential insights these samples could provide regarding Mars geology and its capacity to support life extend well beyond immediate scientific curiosity. Significance: the successful analysis of Martian samples could fundamentally alter our understanding of planetary evolution and the conditions necessary for life. This knowledge has profound implications for future human exploration of Mars and other celestial bodies, as it can inform safety protocols and resource utilization strategies. Furthermore, understanding Mars can enhance our comprehension of Earth's past and future, thereby influencing global scientific priorities and funding. 5. Timeline variability and public perception. The timeline for the MSR is another area where misunderstandings abound. While official statements often suggest a completion date around 2030, internal discussions indicate that delays could push the timeline to 2040. This variability can lead to public disillusionment and skepticism regarding NASA's capabilities. Significance: the timeline's flexibility is crucial for managing public expectations and ensuring continued political and financial support. By recognizing the inherent uncertainties in space missions, stakeholders can better appreciate the complexities of long-term planning in this field. Clear communication about potential delays and the reasons behind them can help mitigate public frustration and maintain enthusiasm for scientific exploration. 6. Risk management and accountability. The emphasis on improved resiliency and risk management in the MSR is often glossed over in favor of more glamorous discussions about scientific discoveries. However, the mission's success hinges on effective risk assessment and mitigation strategies. Significance: highlighting this aspect underscores the importance of accountability in large-scale projects. Understanding the mechanisms in place to address potential failures can build public trust and confidence in the mission. Moreover, lessons learned from the MSR may inform risk management practices in future space missions, enhancing overall safety and reliability. 7. Implications for human exploration. The MSR is not merely about sample collection, it also serves as a precursor to future human exploration of Mars. The data gathered and the technologies developed during this mission will directly inform the planning and execution of crewed missions. Significance: this connection elevates the MSR from a standalone mission to a critical component of humanity's broader ambitions in space. Recognizing this relationship can help the public and stakeholders appreciate the long-term vision of space exploration. Fostering support for current and future missions. Conclusion: the Mars Sample Return Mission represents a multifaceted endeavor that extends beyond simple sample collection. By focusing on the complexities of engineering challenges, international collaboration, budget dynamics, scientific implications, timeline variability, risk management, and human exploration, we can gain a more nuanced understanding of its significance. These often overlooked elements are pivotal in shaping the future of planetary exploration and our understanding of life beyond Earth. As the mission progresses, recognizing and addressing these intricacies will be essential for its success and for maximizing its contributions to science and humanity's exploration of the cosmos. 1. International collaboration and coordination. The Mars Sample Return Mission (MSR) exemplifies a paradigm shift in space exploration through its robust international collaboration. NASA, ESA, and JAXA, among others, are uniting their efforts to achieve a common goal: the return of Martian soil samples to Earth. This mission is coordinated by the International Mars Architecture for Return of Samples IMARS Task Force, which facilitates communication and planning among various spacefaring nations. The strategic alignment of scientific priorities and engineering capabilities across international borders is crucial for the mission's success as it fosters resource sharing and innovative problem solving. Such collaboration not only enhances the mission's scientific output but also promotes peaceful international relations through shared goals in space exploration. 2. Complex engineering challenges. The engineering hurdles associated with the Mars Sample Return mission are unprecedented. The mission involves the collection of soil samples by the Perseverance rover, followed by the design and execution of a retrieval mission that includes launching a rocket from the Martian surface, an achievement never before realized. This phase of the mission is particularly critical as it requires innovative engineering solutions to ensure that the samples can be safely collected and returned to Earth. The need for cost-effective and efficient designs is paramount given the mission's budget constraints. The engineering complexities also highlight the necessity for adaptability and resilience in mission planning, as unforeseen challenges can arise during implementation. 3. Budget management and innovation. The financial aspect of the Mars Sample Return mission is a focal point of discussion among stakeholders. Initially estimated at $3.1 billion, the budget discussions have revealed a broader range of $8 to $11 billion for the entire project, underscoring the need for stringent budget management. The emphasis on innovation is crucial, as NASA seeks to leverage new technologies and methodologies to reduce costs and complexity. This financial scrutiny reflects a wider trend in space exploration where agencies must balance ambitious scientific goals with fiscal responsibility. The financial strategies developed for the MSR mission may set precedents for future projects, emphasizing the importance of cost control without compromising scientific integrity. For scientific priorities and objectives, the MSR mission is poised to revolutionize our understanding of Mars and its potential for past life. The samples collected by the Perseverance rover will provide invaluable data about the planet's geology, climate history, and the possibility of life. The significance of these samples cannot be overstated, as they will offer insights that can only be gained through detailed analysis in Earth-based laboratories. This scientific endeavor not only aims to answer fundamental questions about Mars but also serves as a preparatory step for future human exploration of the planet. The mission's design prioritizes the collection of diverse and scientifically relevant samples, which underscores the mission's role in advancing planetary science and informing future exploration strategies. 1. Apollo Lunar Sample Return 1969 to 1972. The Apollo program conducted by NASA aimed to land humans on the Moon and bring back samples of lunar soil and rock. Between 1969 and 1972, 6 manned missions successfully returned a total of 382 kilograms, 842 pounds of lunar samples to Earth. This program involved extensive international collaboration in scientific research and technology development. The samples returned from the Moon have provided invaluable insights into the Moon's geology, evolution, and the history of the solar system. 2. Viking Mars Mission 1975 to 1982. The Viking program consisted of 2 spacecraft, Viking 1 and Viking 2, launched in 1975 to study Mars. Each spacecraft included an orbiter and a lander, with the landers conducting experiments on the Martian surface and returning data to Earth. While the Viking missions did not return physical samples to Earth, they provided the first detailed images of the Martian surface and conducted in situ analysis of soil samples. The data from the Viking missions laid the groundwork for future Mars exploration and sample return missions, highlighting the potential for life and the planet's geological processes. 3. Sample return from Comet 67P/Churyumov-Gerasimenko 2014 to 2016. The European Space Agency's Rosetta mission, which included the Philae lander, made history by being the first mission to land on a comet. While the mission itself did not return samples to Earth, it collected data and samples from the surface of Comet 67P and provided insights into the composition of comets, which are considered to be primitive bodies that can shed light on the early solar system. The knowledge gained from this mission is essential for understanding the origins of water and organic materials on Earth. Future missions are planned to return samples from such bodies, building on the groundwork laid by Rosetta. The Mars Sample Return Mission (MSR) is poised to mark a transformative chapter in planetary exploration, with its ambitious goal of returning soil samples from Mars to Earth by 2026. This mission, spearheaded by NASA in collaboration with the European Space Agency (ESA) and the Japan Aerospace Exploration Agency (JAXA), involves a meticulous plan divided into 4 key phases. Underpinned by a projected budget of approximately $3.1 billion. Future outlook and predictions. 1. Enhanced international collaboration. The future of the Mars Sample Return mission will increasingly depend on robust international collaboration. The IMARS International Mars Architecture for Return of Samples Task Force will continue to play a crucial role in coordinating efforts across different space agencies. As global interest in Mars exploration grows, we can anticipate more nations joining the initiative, fostering a shared scientific agenda. This collaboration may lead to innovative technologies and methodologies that address complex challenges such as sample retrieval and transportation logistics. 2. Technological innovations. To achieve the ambitious goals of the MSR mission, significant technological advancements are expected. NASA has recognized the need for innovative designs to reduce costs and enhance efficiency. Future developments may include landing technologies, autonomous systems for sample retrieval, and advanced propulsion systems for the return journey. The pursuit of these innovations will likely spur a new wave of research and development in aerospace engineering, benefiting not just the MSR mission but the broader field of space exploration. 3. Budgetary adjustments and economic implications. While the initial budget allocation is set at $3.1 billion, the total mission cost could rise to between $8 billion and $11 billion, as indicated by various sources. The financial landscape of the MSR mission will evolve, with potential adjustments in response to technological challenges, international contributions, and public interest. Increased funding from international partners or private investments may mitigate budget constraints, allowing for a more comprehensive exploration of Mars. Additionally, successful execution of the mission could stimulate economic growth through technology transfer and job creation in the aerospace sector. 4. Scientific breakthroughs and implications for future exploration. The analysis of the Martian soil samples upon their return to Earth is expected to yield groundbreaking scientific discoveries. Researchers will gain insights into Mars' geological history, climate evolution, and the potential for past life. These findings could reshape our understanding of planetary formation and the conditions necessary for life, not only on Mars but also on other celestial bodies. Furthermore, the mission will inform future human exploration of Mars, providing critical data on the planet's environment and resources. Conclusion. The Mars Sample Return mission represents a pivotal step in our quest to understand Mars and its potential for supporting life. Through international collaboration, technological innovation, and a focus on scientific inquiry, this mission is set to redefine our approach to planetary exploration. As the mission unfolds, the lessons learned and the knowledge gained will not only advance our understanding of Mars but also lay the groundwork for future human exploration of the Red Planet and beyond. The success of MSR may very well serve as a catalyst for a new era of exploration driven by global partnerships and a shared vision for humanity's future in the cosmos.